So as I we kind of you can then here at 70 only nil substituent on which it's to and at only the on which leads quantitative. Okay. The question is why the mechanism knows the mechanism. Uh, oh, so, okay. If you ring closing metatic ring on the most accessible site, not this one because it's a free net. Okay, so the first reaction, you intermediate. After that, metal. Okay. When you substitute kin, in fact, you and which increase the alkene to code. So, okay, it is working well, but it's not the only point is working here. Your lactam, you add the ruthenium. Usually, it's ruthenium without air. And the ruthenium vanillin, they want to be so stable. Q substitution here, this and more it is, more you. So this is a way we can condition. Realize this. After that, some we introduce the influence as I already said, on the process. But you have to avoid the formation of this ruthenium fluoromethylidene, otherwise the reaction will stop. Okay? Oh, not stop, but will be very, very, very slow. Okay, next, please. Thank you. So I told you before about when closing metathesis, around 30 publication. We in cross metathesis, there was, when we started, only 5 publications around cross metathesis with fluoride. 2 reactions catalyzed by ruthenium and 3 reactions by molybdenum. Okay, next please. The first one was a pioneering work of Johnson. If you look at the yield, he used ruthenium. It's not good, but it proves that it can work, this reaction with fluoride. Okay? The best result was this one, but the cyclooctane is really strange. So when you are doing the reaction, you really why you got better yield in this case. Turnover number is 11, so it's not very high for this kind. Next, please. In 2015, in JAX was published the work by Akaya and Morizawa. In fact, you have 2 carbons which are stable, and they are playing with the stability of these 2 carbons, and they create an equilibrium between these bonds, and like that, they can do a reaction. And so it's an elegant way. Next, please. And so they use this catalyst, they use 30 to 40 catalysts. You know what the best one? Okay, and next, please. And they were able to do this kind of vinyl fluoride etherenol. And with the hydrogen, they got 72% of NMR. With the 80 to 20 that we ratio with a turn of 7. Okay, there was 2 publications with a ruthenium catalyst. Next, please. Now it is the work done by Schrock and Grader. So they designed the similar reaction to get access to halogenoalkene. Here I just present the result with the fluoroalkene, but they did the same reaction with the chloroalkene, bromoalkene, and fluoroalkene. Okay. So for the fluoroalkene, we published in Science in 2006. With this catalyst, and using the bromofluoroethylene, which is configuration Z, we can have access specifically to the Z fluoroalkene. The same year, with the same catalyst, next please. Thank you. We just change the substrate. They are starting from the E-chlorofluoroethylene, and they publish it in Nature. Okay. And here. Few years later, we change a little bit of their reaction of condition, because in this condition, when they have a phenol or carboxylic acid, it didn't work at all. And so he managed to find new conditions with boron derivative, and first he finds the boron derivative was stick with the alcohol or carboxylic acid, and after that he can do the reaction with the catalyst. And during the separation under silica, they will lose the oxygen boron bond. Okay, and they published that in Langevin in 2008. 2019. Sorry. Okay. Next, please. Okay. So our goal was this one. Take an alkene, take a fluoroalkene. I will talk about different kind of fluoroalkene after, and to get access to twice substituted fluoroalkene, because if you look what I present, it's always di-substituted fluoroalkene. Okay, so we wanted to try to get access for the first time to twice substituted. We wanted to use ruthenium catalyst and not molybdenum catalyst, because the ruthenium catalyst is more practical to use. You don't need glove box, for example. We wanted selectivity, okay? And we wanted also something that we can post-functionalize easily. So easy to functionalize this compound. Next. Okay, so if we look at the source of fluorine atom, you can use fluoroethylene, but it is gaseous, not so expensive, but it's not so easy to use in the lab. Okay? This one is also gaseous, but if you look at the price, it's much more expensive. This one is okay, but it's good, 36 degrees, so it's more practical to you. Price is almost okay. In the lab, we develop a lot of reaction with a 2-fluoroacrylate here, which is a liquid, boiling point 95 degrees. And if you look at the price, it's really not expensive. So we did a lot of hydroxide reaction, for example, with this. Oh, next, please. So we decided to try to use this one to do cross-metathesis reaction. So it is not expensive, convenient to use, and also you have an ester group that you can pass function with the that's it. Next, please. So we're starting to optimize the reaction. Okay. First, we choose two partners which were very effective with the methyl acrylate without fluorine atom. Okay. It works very well. When you have fluorine atom, you get nothing. We get nothing. So we change methyl and we look at the book of Vela, which is one of the most specialized guy in metathesis reaction, and we said that when it doesn't work, you have to go further to the reactive site of your alkene and to put a substituent not directly connected to the alkene, but you can add one more carbon or more carbon to have better reactive. So when we use benzene instead of helium, we have some traces of compound. Traces, that means that well, but with the TMS, we can get 8% with the product. With the phenylbutane, we get 22% yield, and with the lactate, 16% yield. So we decided to use the phenylbutane because it was more easy to look at under UV, you know, under the light for the TMS. So we decided to optimize the reaction with next. So using the phenylbutane with a 2-fluoroacrylate, at 40 degrees we get 22% yield. If we increase a little bit of the temperature and 80 degrees, we get 58% yield. Oh, okay, I forgot to tell you. This is the main product we have. It is the product we targeted, okay? During the reaction with ruthenium, you can form ruthenium hydride. If you form ruthenium hydride, you can have side reaction, and you can have finally the bond with one carbon less or one carbon more during the process. So when I put the ratio here, it's the ratio between 2A, it is the desired product, and the other side product. Okay? Next, please. When we use 1 mole % instead of 10 mole % of catalyst, we got almost exactly the same yield, but with a better ratio. The reason is just you use less ruthenium, so you produce less ruthenium hydride, so you have less side product. Next, please. When we use 2 equivalent of this one instead of 1 equivalent, we get 85% of isolated. Next, please. Next. Okay. If we increase the temperature, the catalyst will be more degraded easily. So it's not as good as at 80 degrees. And in 1 hour and 7 hours, it was less effective than 15 hours. So we choose this condition as the optimal condition to do the react. And next, we study the scope of the react. Okay, so the phenylbutane, you can make power substitution with electron donating group. You can have access to 76 to 88% yield, and you can see that the ratio is always in favor of the compound we want. Next, please. Okay, you can have halogen atom, some kind of yield, but fair yield, good yield, selectivity. Next, please. And you can also use electron withdrawing. No problem. So it is in power position. We can do the same in meta position. Next, please. Okay, with methyl from 1 or 5-fluoromethyl. Yields are fair to good, with good ratio. Autocyclicity is the same. And you can use also next, please, some heterocyclic compound and type of compound. So we were happy with that because it was the first time that we can use ruthenium to form twice as substitutive fluoride. Okay, we can also use alkyl instead of phenylbutane. Okay, so different kind of factoring. You can either use pretty good. You can use this one and this one. If you remember, we got only twice in the first table, and with this new condition, we get 60% of prospect. Next, please. During the reaction, we form also the self compound of this one, of the phenylbutane. So we isolated it and put it on the reaction to see if the reaction can work on internal alkyl. And it can work, actually, 58 or 68 situation. So we decided to use other internal alkyl. I just put here some short examples. So with polyat compound, D or E, we can have access to different compound, which is quite interesting. This two acid group, different acid group. This one is more active with the fluorine atom. Next, please. And you can use also the air tape, and you can get this kind of compound with really good yield and ton of 150. Again, I repeat myself, a ton of 150, it's ridiculous for metathesis reaction, but not for metathesis reaction with fluoride. Okay, it's really good ton of unknown. Okay, so why do we have a good stereoselectivity? Next, please. Okay. If we want to have access to the Z1, we have to have this kind of access. It is possible because we have steric and electronic match here. So we got this kind of intermediate, and we have only the Z isomer. We never saw the E isomer in this kind of way. If you want to have the E isomer, you have to reverse the approach of your alkene, and you have steric indwelling between the L group and the ester group, so it doesn't work. Next thing. And also, if you reverse here the alkene, you have steric indwelling between the chlorine atom and the fluorine or ester group, and so we never saw this kind of intermediate. Hopefully, because if you form it, the reaction was done. Okay, so to resume, we developed this kind of reaction of 3 examples to 12. It's not so high, but 98% of yield. Only Z is that isomer, and we get access to an ester group that you can easily post-functionalize. Next, please. There is some limitation. We cannot have basic or acid compound on or substrate, otherwise the reaction is not working. And if you have 2 steric bonds, for example, with tyrene or conjugated double bond, it doesn't work easy. Next, please. And few months later that we published that, Oveder and Schrock again published in Nature Chemistry in 2022 this kind of reaction with this time is dichlorofluoroethyl E and Z, and the other stuff with these compounds, which are very interesting because here you can easily post-functionalize the chlorine atom. Next, please. Okay, thank you. So I finished with my first part. I start the second part. I don't know how the time is because it's okay. Okay. The second part deals with photochemistry, and it was done by Solène Morin, a PhD student. Next, please. So the idea was it's really easy to do the gem bromofluoroalkene, but we use it a lot for cross-coupling reaction. And here we wanted to produce fluorovinyl radical and to see what we can do with that. Next, please. Knowing that fluorovinyl radical is really stable, it's configurationally stable. So it was shown by Gally a long time ago. You can find this radical, and you can add this one, and you preserve the configuration of your double bond. Lauder later do this kind of reaction. When you have a fluorine atom here, you have a Z compound, you got exclusively the hydrogen as the bromine position, and you don't have a mixture of E and Z compound. If you have instead of a fluorine, you have a methyl or a cyano group, you will end with a mixture of 1,1 E and Z compound. So that means that the fluorine atom, the fluorovinyl radical, is very stable in the configuration. Okay? Next. Okay. So I already told you about the interest of fluoroalkenes, but what we wanted to do is to couple, in fact, this fluorovinyl radical with phosphide. Next, please. So I already told you that the fluoroalkene is a mimic of amide, but we can see further if you have nitrogen, oxygen, or sulfide or sulfur atom here, it can become a mimic of UA carbamate or S2 carbamate also. If you have a boron or silicon atom, it can um, become a platform for further post-functionalization. If you have a phosphorus atom here and a phosphonate, it became a mimic of phosphate. So it is really interesting. Next, please. It was shown by Dumitrescu, for example, in this kind of sugar, when they replace this part by a fluorophosphonate, they show that they have an increase of stability and biological activity thanks to this phosphonate, this fluorophosphonate. Next, please. Zhang also shows that with a K-lipid, and he showed that adding a fluorophosphonate instead of phosphate, he gained in metabolic activity, and you have a stable mimic of phosphate. Okay, next, please. Okay, so how to do this kind of reaction? Next, please. In fact, you can find plenty of reaction on photocatalysis with difluorovinyl. Okay, this is an example here where you can replace one of the fluorine by an alkyl group, for example, with the Manchester here. But we wanted to use our substrate, the bromofluoroalkene. Next, please. So to design this kind of reaction, we base our condition on the conic one. He described a photocatalytic reaction with bromoarine, and he got aryl phosphonate with yield fair to very good yield. So we did what? We took exactly the same condition and we apply it to all substrate. Next, please. And applying this condition to all substrate, we got 6% of yield. It's not good, but it means that it works. So you can improve it and get better yield. Can you go further? Okay. So we did a lot of optimization. I just show you some example. Here it is optimization with the photocatalyst. We use a lot of photocatalysts with different irradiation. And finally, next please, the best result was with a methyl acrylinium, the Fukushima catalyst. And we got 63% of yield, which is quite good, actually. So we use this reaction to the scope of the reaction. And in fact, what was interesting also here, usually we start from easy mixture of this compound because it's really difficult to do this compound under one form, okay? You can do it, but you have to eliminate one of them if you want to have the other one. So here we can start from a mixture, and we can have access to the E or the Z. Usually we can separate both, so we can have access to both quite easy. Okay, so the yield here might be quite confusing, okay, because if you add it, it's more than 100%. But the 60% of E, it's from the 94% of E you have in the mixture, okay? And the 63 here, it's from the 51% of the Z we have in the mixture. That's why you have two yields, one for the E, one for the Z, and it's more than 100%, okay? So you can have electron withdrawing group. It works quite good. Next, please. We can do it with halogen atom, same kind of yield between fair and good yield. Next, please. We can do it with electron donating group also. Good result. Next, please. And we can do it with quite interesting substituent like BP or also alkyne, this kind of alkyne. Next, please. So it was in power position. Now it works in meta or auto position, even if here we have 48% of yield, we cannot separate it, for example, okay? But we have a mixture. With this one, which is kind of really in dirt, we have only 70% yield. We can do it with heterocycle, next please, or with quantitative system. And also we can start not from, because this was done from aldehyde, but we can do it also from ketone, and we can have access to tetrasubstituted fluoroalkene in this case, with fair yield. Yeah. Okay. Next, please. We have reluctant substrate. It doesn't work with nitro, but when you are doing photocatalytic reaction, nitro usually is not so good substrate. And it doesn't work at all with alkyl group, unfortunately. Next, please. Okay. So to try to know what's happening in the reaction, we did some Stanvormer experiment. It's what quenches the emission of the photocatalyst. We need to know that to know what is the first reaction for catalytic cycle, actually. So we mixed the photocatalyst with the phosphide. If we increase the concentration of the phosphide, nothing happens. So that means that it's not the phosphide who quench the photocatalyst. Okay, next please. Same with the substrate. Substrate and photocatalyst does not interact. Next please. But with the IPA, you can see that you can quench the emission of the photocatalyst. More it is concentrated, more you quench the emission of the photocatalyst. That means that the first reaction is between the photocatalyst and the DIPA. Next, please. Okay, so what is the reaction? You have your photocatalyst, you excite it with a photon, and you have a single electron transfer to get this radical cation and the photocatalyst radical. So here we think of two possibility of mechanism. Next, please. One is based from Leonori in Science 2020, which is demonstrated the XAL, I don't know, the XAL transfer, the halogen atom transfer. Okay, he showed that it can happen with this kind of radical cation. Next, please. And to do that, it is that with this kind of photocatalyst. Problem in all reaction. Next, please. The reaction doesn't work with this photocatalyst. So we preclude the XAL mechanism. Next, please. So the most simple one, we think that, okay, we have the photocatalyst, radical photocatalyst, and so we can reduce directly or bromofluoroalkane. But if you look at the thermodynamic energy, that means that you have a delta G of more than 23 kilocalories per mole. That means that it's not possible to do this kind of reaction. So what we think, what we propose, next please, if we have a double activation of our photocatalyst with a double photon, and we make this kind of catalyst, so we still have to prove it, okay? We don't know if it is that, but it is the only explanation we find to explain the reaction. This kind of double activation is known with other photocatalysts, but not with this simple one. Okay. When you have a double activation, it is high reductive photocatalyst. So we can imagine that we can reduce our bromofluoroalkane. If you reduce it, you form the radical anion, and you lose, next please, after that the bromine atom, and you form the fluorovinyl radical, which can react with the phosphide to form the desired compound. And after that, the radical the alkyl radical can be catched by your radical cation here. Okay. Okay, so to resume here, we develop the first. I put the first into, I don't know how to say in English. In French, we say guillemets. Okay. Photoredox catalyst to get access to fluorovinyl phosphonate in mild condition without metal. It's fair to very good yields, and we can have access to both diester or isomer. So it's quite interesting. Limitation, it doesn't work with alkyl derivatives, and mechanism is still under investigation. I put it like that because the same year, next please, we publish In the same volume of organic letter, we find this reaction, which is also a photocatalytic reaction to get access to fluorovinyl phosphonate. So it's not the first. It was the two first reaction to get access to the fluorovinyl phosphonate by photocatalysis. Okay, next please. Okay, so I have to thank all my collaborators, Jean-Philippe Bouillon, Annie-Claude Gaumont, Marc Mauduit, Sami Ladda, my student, of course. Next, please. This is our team, and I would like to thank again Conacyt, ECOS, and you for your kind attention.
Okay, thank you, Dr. Samuel. Okay, so we have time for questions.
Okay. Go.
So I have a question. Why do you use 10 equivalents of phosphonates?
of phosphine.
Phosphine.
Yeah,
Sorry, phosphine.
because we can use less, but it's not
It's
so. It is possible, but the yield decreased actually. So we don't know exactly why we need 10, but we need a lot for the reaction to proceed well. If you use, for example, two equivalent, it works, but we will get 20% of yield instead of
Yes.
60 or
Yes,
70%. Yeah.
because this morning I think so we talk about the atomic economy.
Yeah, 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 yeah.
What
Yeah.
happening with the excess and
Yeah.
pollution
Yeah.
also.
The reason is just because the yield decreased, actually. So we use 1, 2, 5, 10, 20. And the best compromise was with 10. But I agree with you, it's a lot.
It's a lot, but
But,
okay. My second question, because we don't know what happened with this kind of reaction. What does it mean stone?
turnover number is a number of catalytic cycle
okay,
you can
I know.
sorry.
No,
Okay.
it's for me because
Okay.
we don't know exactly what happened
For
with
example,
this reaction.
for example, when I say 100 of ton, that means 1 mole of catalyzer can make 100 cycle.
Okay.
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 So in metathesis reaction, you can have a ton of 1 million, for example. Okay.
Okay.
So here with 100, it looks ridiculous, but again, with the fluoroalkene, it's really good.
Okay. Okay. Thank you so much.
You're welcome.
Okay, more questions?
The reaction condition in
Of
the
which one?
first part of your
The
lecture.
metathesis reaction, okay.
No, the first time with ruthenium.
The ring closing metathesis, okay.
The reaction condition was, do you use a reactor for the reaction, or
It usually it's a shield tube. It's a tube sealed.
okay?
Yeah.
Because in one of the slides you have the condition of 80 degrees.
Yeah.
And the solvent is the chloromethyl.
Yes, so it is the second one. So the pressure is really important also. Yes, you use seal tube with dichloromethan.
Okay.
So that increases the pressure, and the pressure is really important in metathesis reaction. So it was with the cross metathesis reaction. Yes, you're right. If you did it in open, it works, but the yields decrease a lot. So we need to have a seal tube.
And in microwave conditions, you can use another the same.
It was
You can heat with a
yes,
solvent
yeah, but
boiling point lower than your.
But for the cross metathesis, this was not in microwave. The microwave was with ring closing metathesis. In this case, we can do it in microwave or under heating, usual heating, but the reaction is just longer. But it worked well also. Thank you.
Entonces, procedo a leer la constancia, ¿vale? El Departamento de Química de la UAM Iztapalapa otorga la presente constancia a Dr. Samuel Covec Boneag por impartir dentro del ciclo de seminarios del Departamento de Química del trimestre 25P la conferencia Fluoroalkenes, Catalytic, Access and Application, el día miércoles 30 de julio de 2025. Firma el jefe del departamento, doctor Juan Marcos Esparza Schulz, y su servidor, el coordinador de seminarios, Víctor Manuel. Casa abierta al tiempo, Ciudad de México, julio de 2025. Muchas gracias por su asistencia.